So here is some data that I took by dropping that weight off of the table, which you do have a video of. Now, this is the data that is tracked in the iOLab, and we're looking at one-dimensional motion. Now, one of the things that you have to understand about the iOLab is its orientation. So when we're looking at the back of the iOLab, there's actually an X and Y and a Z coordinate system so that we can look at it. And it turns out that as I'm moving the iOLab towards the edge of the table, it is actually moving in the negative Y direction, which is exactly what you can see here, because this is giving me a position plot. So where I started at 0, it's moving in the negative Y direction, or to the right-hand side of the table, but the way the sensors are set up in the IO device, it's going to go out that way. Now I want you to look at the motion in our position graph. So this part here is while the little IO device was in motion. So we have this little IO device in motion, but I want you to see that this isn't a straight line. This is a curve. And we can actually see that it's going to be a polynomial, because if we know our equations of motion, the change in position is equal to the initial velocity times time plus 1/2 the acceleration that the object is seeing times time squared. So the way my device is set up, we're moving in the negative Y direction. We are knowing it's going to go as time squared, so we're going to get a polynomial function that in this case is squared, and we can actually see that in the motion of the graph. Now, this becomes a little clearer when I'm looking at my velocity equation. And when we look at our equations of motion, we have our final velocity is equal to our initial velocity plus acceleration times time. But you can see right here, we've got essentially a straight line. Now, it's got real data, so we're going to see a bit of variation. But I've got a straight line, and that straight line on a velocity versus time graph is going to be an acceleration. And in this case, we are dealing with a constant acceleration, and you're able to see that in the graph. But so now if I'm looking at my acceleration here, I'm also getting my graph as well, and I'm showing my acceleration in the Y direction, and we can actually see that it's relatively constant. Now, this information here past this point is after I stop the motion. So we're looking in real time at one-dimensional motion using the IO device. And we can actually get a slope of this line. So if we wanted to look at this, we can go here that my initial velocity is 0, and my initial time is at 0.623 seconds. And so my initial point on that graph is 0 meters, 0.213 seconds. Now, if I come down here, or 0 velocity, this is 0 meters per second, but now I come down here, I have a negative 0.627 meters per second, because that's what our data is in, and I'm at 1.64092 seconds, and I can calculate that slope. Now, it's a negative velocity because it's moving in the negative Y direction in this case. So let's do that. Let's calculate the slope. Remember, the slope is rise over run. So my rise, or in this case, my change in my slope is, it's going in, my final velocity is a negative 0.627 meters per second. We subtract our initial velocity, which is 0. So I get a negative 0.627. And I'm going to divide by my change in time. And my change in time was 1.64 minus 0.623. And if I do that, I get a slope of a negative 0.617 meters per second as it's rolling across the table. And again, meters per second squared, because that's my acceleration here. My acceleration is in a negative direction because it's going in the negative y direction. I've got a constant, so we can take that slope, and I can come in here and I can compare that with the kind of the range in here, and sure enough, it looks like we're getting reasonable data. So that will help us with one-dimensional motion. And we're going to look at it another way as well.